Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics by Howard D. Curtis, 4th edition, and I'm up to problem 2.39. And 2.39 says, for a hyperbolic orbit, find the eccentricity in terms of the radius at periapsis and the hyperbolic excess speed v infinity. So to do this, we're going to start with the energy equation for a hyperbolic orbit, which is 2.39. So velocity squared over 2 minus the gravitational constant over r equals the velocity excess over 2. And this is, we're trying to do it at periapsis, so it's the velocity at periapsis and the radius at periapsis. And the radius at periapsis is also equal to a e minus 1, so semi-major axis times the eccentricity minus 1, and that's just a simplification when theta is equal to 0. If we put this back into here and rearrange, no, sorry, we don't even want to do that. That there is equal to the gravitational constant over 2a. We rearrange for a, we end up with a equals rp over e minus 1, and we put that in here, so we get velocity, and that's squared, equals mu divided by rp e minus 1, which is equal to mu on e minus 1 over rp, and then rearrange for e, so v rp equals, divided by mu plus 1 equals e, and that is what is given in the answer. So that's that, not very difficult. And then 2.40 says a space vehicle has a velocity of 10 kilometers per second in the direction shown when it is 10,000 kilometers from the center of the Earth. Calculate its true anomaly. So this is the Earth. This is the point on the orbit. It shows on the picture it's 120 degrees here from the Earth, and we know that the azimuth is at 90 degrees, and so we know that this is 30 degrees and this is 60 degrees, and so from that we can just say that the velocity azimuth equals sine, so there we go, sine equals the opposite over the hypotenuse, and that gives you your azimuth, and then from your azimuth you can get h, your angular momentum, because that is just equal to velocity azimuth times r, which we have 10,000 kilometers, and then e is equal to the square root of h squared over a mu plus 1, and that's just rearranging the equation, which relates the semi-major axis and the eccentricity, and that is originally E equals h squared over mu upon 1 over e squared minus 1, and you can find that in my hyperbolic orbit trajectories video and in the book, obviously. So once you've got the e, getting theta is just another rearranging equations, so cos inverse h squared over 2 r gravitational constant minus 1, and all of that is over e, and that gives you 50.94 degrees, and the book is 51 degrees, so that's that. If you think I've made a mistake or you have any questions, leave them in the comments below. The MATLAB will be in there as well in the description. Thank you very much. Goodbye.